Welcome to Chapter 16, Section 3, Part B. Okay, we're just going to be looking at the very last page of the section, so just this 579 page, okay? So what we're going to do is we are going to identify the four properties associated, which means connected, with a conductor in electrostatic equilibrium. So to understand what's happening, we need to remember that conductors are materials, usually a metal, that has electrons that are free to move around, okay? So if a conductor has excessive charge, and in this case it does need to be electrons, okay? It can't be protons in this case. And it needs to have a not zero charge, okay? So this is, the charge has been added or removed, really it has been added, okay? So the charges then, they'll try to spread out within the material as much as possible, and this is because like charges repel. So all these electrons in the material are repelling each other, trying to find as much space as they can for themselves, okay? Once all the charges stop moving, okay, once we hit that point, that is what we call electrostatic equilibrium, okay? So all the electrons have stopped moving, everything is balanced. That is what we're going to be looking at, okay? So we're going to look at conductors in electrostatic equilibrium, meaning the charges have stopped moving. So when we look at these then, conductors in electrostatic equilibrium have four unique properties, okay? So the first one is inside the conductor there is no electric field, okay? So inside here, if this is my conductor, if I just have a round metal sphere, on the inside here there's no charge, okay? And one way to think about that and understand that is if there was a field, okay, if there was an electric field inside, right, electric fields cause movement, right? So having an E field not equal to zero causes a force, which causes acceleration, so it moves, okay? So it has to be zero, otherwise the charges would still be moving, they would still be bouncing around in here, and then it would no longer be in electrostatic equilibrium, okay? So once it's in electrostatic equilibrium, there's no electric field inside the conductor. Okay, we do get a field outside the conductor though, because we have the charge here all on this surface, okay? And what that means is that the charge sits on the surface or the outer edge of the conductor. Okay, so there's not going to be any free electrons floating around in here, because if so, they'd be affected by some field and they would move, okay? So all the charges end up sitting on the surface, which gives an electric field outside, okay? And really I should change this to say not no charge, but no electric field, okay? Which comes out to about the same thing as a charge, okay? It's close. But you do get an electric field out here. So not in there, but yes, out here. So the next thing is similar to when we talked about point charges, and that is that the field lines will extend outside of the conductor, perpendicular to its surface, okay? So here we just have a simple round sphere. It's like a really big charge, right? And we know all these charges are sitting on the outside. There's no field inside, but we get all of these electric field lines produced because there is an electric field on the outside, okay? And the rules for these fields are the same rules, okay? Same rules as we learned before for drawing, okay? I should use a capital E there, okay? So because they're always perpendicular to its surface, I just want to point out what that would look like on a weird surface like this, okay? So the way you find out the direction it goes is you draw a tangent line to wherever you see it, right? Okay, so it's tangent to this point here, so my E field will go in that direction, okay? And I can do the same thing in here, right? Here's my tangent line, and I'm going to get an E field in that direction. Okay, and I could have a tangent line here, and so my E field would go in that direction. Tangent line here, my E field will go in that direction. And so on, all the way around. So it's always going to go perpendicular to that tangent line, and that helps us identify the direction, okay, that the electric field is going. Okay, so this is going to matter in a minute because this brings us to our number 4 characteristic of conductors in electrostatic equilibrium. And that is that the electric field is strongest where the surface curves the most. Okay, so I drew a picture here that has some curves, right? It's got some kind of flatter areas, and then it curves more. Then over here it curves a lot, and then it comes out to this point here, okay? So if we looked in, we could think of this as just a really, really small curve. And I just wanted us to pause and think about why we're going to get the strongest electric field. Okay. So if I have these two charges here, right, they're trying to spread out and get away from each other, okay? So they're giving a force on each other, so the force is going to be in this direction and this direction, right? So that's why they're going to spread out. But when we get down here, right, the direction between them, right, is in this direction, okay? So that means the force on this one is going to be going this way, and the force in that one is going to be that way. And that means you can put a lot more electrons down here because the force is going off the material and it's not going to fly off. Whereas here the force is direction parallel to the material. Okay, so same thing if we had electrons here. If we had one here and here, the force would be that way. Okay, so in red here, all my arrows, these are the force of repelling. Okay, so because these aren't along the surface, you can get a lot more of them. What that means is if we take this now and we go here where I haven't blown it up and I start to draw my electric field lines, I'm going to get a lot more electric field lines on the point of this, okay, than I am in other areas because remember, it's stronger where you have more electric fields. So here we've got a kind of flat area, so we're only going to have a few lines. Right here it curves a little bit more, so we're going to have a couple more, and then they're going to space out again. And here we've got a pretty even curve going on, and then it curves a little more strongly, so they're closer, okay, and so on and so forth. Okay, so the key here, the electric field, and you show this, right, with field lines, is strongest where the surface curves the most. Okay, so I just want to make sure I realize this might be confusing, right? When I draw these arrows up here, I'm talking about the force. Here, I'm talking about field lines. I should have used a different color. So make sure you note that difference. Okay, so more field lines where the electric field is strongest, which is where the surface curves the most. Okay, so let's just make sure, and I've got a question for you here to make sure you understand. So suppose that we have a Van de Graaff generator, which was this big ball machine that I did with a demo in class, okay? And it gathers a charge, okay? So that charge is on there, and then we're going to turn it off, okay? So the charge is still there. It's still a charged thing because we haven't touched it, okay? And it's allowed to reach electrostatic equilibrium, so the charges are not moving anymore. What would we say about the charge? The charge, A, resides both on the surface and throughout its volume. B, resides means is, okay, so it is in both. It is, okay, so it is mostly inside the sphere and only emerges or comes outside when touched, or it resides or exists only on the surface of the sphere. So go ahead and take a minute to think about that. Okay, so hopefully you answered C. Okay, it's only on the surface, and this comes from our number 2 fact that we learned. Okay, charge ends up only on the surface of the sphere. There will not be any charge inside. All right, so that's the end of section 3 for chapter 16. See you guys in class, and I'll talk to you there.